Hi everyone, this is Kiranmai from HNS department. Today we are going to have a look on Davison-Germer experiment, which is an proof for the uh, existence of matter waves in nature. So coming to the experimental arrangement for the Davison-Germer experiment, you can see on the screen this experimental arrangement consists of one electron gun, which is connected to a potential. Okay, this electron gun will readily give you a beam of electrons which are fast moving. So it is ready to produce fast moving electron beams. These fast moving electron beams, we are make them to flow through two slits S1 and S2. The uses of these slits is to make them fine and sharp. Fine and sharp. How this can be done using these slits? These slits will allow only only the electron beams which are in single direction, and the uh, deflect or scattered electron beams cannot be passed through them. So these slits will help us to make this scattered electron beams into fine, sharp, single directional electron beams. These fine, sharp electron beams are made to fall on a target material. This target material here we are supposed to consider it is a nickel crystal, which is having an atomic spacing of 0.9 angstroms. Okay. And the scattered radiations from this target material are supposed to be collected using one chamber called as ionization chamber. This ionization chamber will allow those electrons, and it collects them. Since the gases are present inside the ionization chamber, electrons which are collected in this chamber will ionize the gases present in this chamber, and in turn they will produce current which was recorded in a galvanometer. And this chamber, which will collect the reflected electrons from the target material, this chamber is movable on the graded scale, which is a circular graded scale, whose angles can move from 29 degrees to some 65 degrees. Okay, so this is the experimental arrangement where all this arrangement is placed inside one evacuated chamber. So let us see in steps how the uh, experimental arrangement can be done. The experimental arrangement mainly consists of what? Electron gun, which produces fast moving electron beams passed through two slits S1 and S2. The beam of electrons are directed to fall on a large single crystal of nickel having atomic spacing of 0.09 nanometers, which is known as a target material T. And the reflected electrons or the scattered electrons from the nickel crystal are collected by an ionization chamber, which is connected to galvanometer to measure the current. Okay, and the ionization chamber, which is connected to galvanometer, is movable on a graded scale S between angles 29 to 90 to receive the reflected electrons from the target material. This is the experimental arrangement as we can see on the screen. And we have to remember how the electrons are getting converted into current, because the electrons which are collected in the chamber will ionize the gases which are present in this chamber. Hence it is called as ionization chamber. After ionization, the current will be produced, which will be seen or recorded using a galvanometer. Okay, then there will be a doubt that since electrons are striking the target material, there is a chance that electrons can be emitted from the target material also. So the electrons which are getting incident on the target are called as primary electrons, and the electrons which are emitted out of the target material are called as secondary electrons. Two sort of electrons will come out here. One is the electrons which are incident on the target material will get reflected back, and due to the incidence of electrons on the target material, some of the electrons from the target will be ejected out. Those are called as secondary electrons. But here the current should be produced due to primary electrons only. That can be done using by applying retarding potential, so that this chamber can collect only the primary electrons but not the secondary electrons. So potential is provided there in such a way that ionization chamber collects only the primary electrons, and the secondary electrons are not collected by it. Okay. So a retarding potential is maintained between them, so that only fast moving electrons coming from the electron gun may enter inside it, and the secondary electrons, if any, generated at the surface of the nickel are stopped by the retarding potential. Thus galvanometer connected to the ionization chamber shows diffraction due to the electrons from the electron gun only. These are the experimental arrangement steps for which we can prove the existence of matter waves. Then coming to the working of this experimental arrangement, keeping the accelerating potential as constant, just the ionization chamber is moved over the graded scale, which is provided over there, which can move from 29 degrees to 90 degrees. At each and every angle, the galvanometer current is noted, and the graph should be drawn between various positions and the current produced in the galvanometer. And the experiment is repeated for different accelerating potentials, and we can draw the graphs between angle and the potential. So as you can see, in the experimental arrangement, this ionization chamber can move on the graded scale. Yes. So as you put it at certain position on the graded scale and take the ionization current, how much current will be produced in the galvanometer, record it. Again, the position will be changed. Again, the position will be changed like this. For different angles, we can we can record different currents, corresponding currents in the galvanometer for a particular potential provided. As you change the potential, the electron emission or the reflection also changes. So according to that, for different theta values, I value also, current value also changes. So those values will be recorded, and graphs are plotted between theta on x-axis, I on y-axis at different potentials. Like on the screen, you can observe at 44, 48, 54, 60 volts. They had drawn a graphs between angles recorded on the graded scale and the current produced in the galvanometer. As the input potential is increasing, from the graph you can see that the bump which is produced in the graph, a peculiar bump which is produced in the graph, it is becoming more prominent as the potential is increasing from 44 to 48 and from 48 to 54. But at 54 you can see that there is a prominent bump in the graph at an angle of 50 degrees. At an angle of 50 degrees. Now beyond 54 volts, if you increase the potential, this bump is getting vanished. That bump is getting vanished as we go beyond the 54 volts potential. So the peculiar behavior is observed at a potential of 54 volts and for an angle of 50 degrees. By making this one as a prominent node, they had calculated the de Broglie wavelength, and they had calculated the wavelength using de Broglie wavelength and also Bragg's law. That is, one is works like a wave nature, another one works like a particle nature. So comes to the observations from the graph. With increasing potential, the bump moves upwards. The bump becomes more prominent in the curve for 54 volts at 50 degrees angle, and at higher potentials, the bump is gradually disappearing. These are the three observations what they had seen from the graph. Now let us calculate the wavelength using de Broglie hypothesis. We are just taking for electrons, that is particle nature. Lambda is equal to 12.26 by root V Armstrong. Since we are talking about electrons, this formula can be applicable. Okay, so as we had seen peculiar behavior at a particular potential called 54 volts, so in place of V, just replace 54, we can calculate its wavelength as 1.67 Armstrongs. This is particle nature. Now let us see using the Bragg's law. So according to Bragg's law, you know that lambda is equal to 2d sine theta, where lambda is the wavelength, d is the atomic spacing, and theta is the diffraction angle. So to find out the diffraction angle, let us see that the peculiar behavior is seen at the 50 degrees angle. So incident electron will get reflected back at an angle of 50 degrees. So if the total angle is 50, this will be 25. On the other side, it will be 25. So if this angle is 25, the rest of the angle will be right angle minus 25, that will give you 65 degrees. This was the diffraction angle. So substitute them in the formula. 2 into D. D is the atomic spacing of nickel crystal target. For the nickel crystal, the atomic spacing is 0.09 nanometers. Na? So 0.09 into 10 power minus 9 into sine 65. If you go for the mathematical calculations, the value will be like 1.63 Armstrongs. So you can easily say that both the values from the de Broglie wavelength 1.67 and from the Bragg's law, you are having 1.63 Armstrongs. Both the values are in good agreement. So we can easily say that de Broglie concept of matter waves is confirmed. That is, the existence of matter waves is proved. This is called, since this complete experiment was explained by the two scientists known as Davison and Germer, the experiment is called as Davison-Germer experiment. Thank you.